We're electrical and computer engineering students at Oregon State University.
We're seniors of the class of 2020.
And we built an RF time-of-flight based autofocusing system.
Hi, my name is Chelsea Starr. I was in charge of the project budget. I did tag design and layout, button firmware, and the power budget.
My name is Suyang Liu. I organized weekly meetings. I designed the hardware for the motor and driver. I implemented code for the motor driver, and I developed the basic structure for the tag firmware.
I'm Jordan Baxter. I worked on project management, anchor design and layout, enclosure design, and lens calibration and distance measurements algorithms in the firmware.
In this video, we're going to talk about the problem that this project addresses, give a walkthrough of how the system works, show the system in action, and discuss future revisions.
Currently in action in sports photography, filmmakers are limited to using infinite focus. Infinite focus is where everything in the frame is sharp, regardless of the distance to the camera. These two photos are examples where infinite focus have been used. As you can see, the subject is in focus as well as the background.
The current solution to this problem is called follow focus, where a second operator stands to the side and ensures the subject remains in focus for the duration of the scene. Our system aims to replace this operator with automated RF time-of-flight measurements.
Our project is a hardware-based solution that utilizes ultra-wideband technology. Ultra-wideband is used in cutting-edge consumer electronics, and even then, only in top-of-the-line products. It features a 10 cm accuracy, up to 50-meter range, and works even when line of sight is temporarily lost. Our system is implemented with two devices, one worn by the subject and the other is mounted to the camera.
This diagram shows how the focus system works. The two devices communicate with each other to determine a time-of-flight measurement, which is used to calculate distance. This distance value is used to focus the lens.
The devices are similar. Both feature an ultra-wideband transceiver and a Nordic microcontroller. The device attached to the subject needs to be mobile, so we've implemented a battery and a battery charger. The device mounted to the camera needed to be able to turn the lens, so we implemented a stepper motor and a motor driver.
On startup, the photographer will need to calibrate the lens using lens characterization mode. After this, the system will enter active mode, the main mode of operation, where focus is continuously maintained. We have also implemented a zeroing mode, which will be useful in future revisions when the lens profile can be maintained through power cycles. This mode will enable the user to quickly set up the camera without needing to recalibrate.
There are several things that could be changed for future revisions of this project. The first would be an additional microcontroller that would allow for greater programming flexibility. Non-volatile memory would allow lens profiles to persist through power cycles. Larger buttons would make the device easier to operate. Compatibility with standardized camera power supplies would allow for seamless integration. And finally, a more rugged enclosure would increase reliability in sports action settings.